You both can present the same thing twice. There could be slightly different views on the same subject. So thanks much for your effort, and I see that there are champions in the class who have already submitted the slides for tomorrow. So the main goal is that everyone submits now, and I will try to help as much as I can. The subject of today's stuff is what is in the boxes. And since Rebecca, you are doing it next Tuesday, you have a little bit more time, so you can prepare, invest like more small intervals of time, and maybe Gwendolyn is not here today, and hopefully she will come today and tomorrow. But just in case, you can cover reaction coordinate and transition state search if you can. Just try your best. I do have something about it in today's slides, but practically I don't believe that we will be able to cover all this today. But the reaction coordinate is important to those of us who really want to be chemists or do some chemical applications when chemical bonds are formed or broken. If you're more like looking onto using existing materials like engineers rather than looking for chemical reactions, it is of secondary importance. Maybe if you design sensors when adsorbates are coming and changing conductivity. So first we will focus on this part, and then I believe that there will be time for this thing as well. Last time we did enjoy, I hope everyone enjoyed, very important part, how to convert set of large number of molecular orbital energies into density of states, and how to plot molecular orbitals which are composed of atomic orbitals in as three-dimensional pictures. The skill that we got last Wednesday and that you have confirmed by completing homeworks, a vast majority have completed it. Maybe there is one or two missing, but I see that the class got it. It is a universal skill, but there are a few exceptions when the skill that you have accumulated last time and the skills that will be presented tomorrow by Raju and Salim are not applicable. When following the protocols that we have learned, will fail, will bring a system to either panicking and not completing calculations, like stopping, or to giving wrong result that will disagree with the experiment. So anyone has an idea what is the challenge that when density of states and molecular orbitals as we studied them last time will not work. So when we did an example, when we looked on the list of orbitals, how many electrons were sitting on one orbital? 2. Is it always so? It was always so in what we did, but is it always so in the nature? So in which examples this 2 electrons per orbital will fail, will not work? And how important it is? Maybe it is so rare that we don't care.
Excited state.
Huh?
Excited state. When this.
Okay, but for excited state, I'm sure that this is not a strong. You can still believe in 2 and 0 electrons, that it will be good calculations. But in the ground state, which systems will give a failure of this 2 electron per? Which class of materials? Which class of
system is non-stable, not stable.
Okay, radical, chemical radical when there are like broken bond, lone electron pairs,
Yeah.
something like CH3, like stable molecule is methane, CH4. If you rip off one hydrogen, this methane will be unstable, and if you try to do this protocol for it, it will either not work or it will give something wrong, because it will be an odd number of electrons, so-called open shell. What other examples when an orbital may have between 0 and 2 electrons? When only one electron comes, one unpaired electron comes to a certain orbital. You may have this idea from your general background. Do not hesitate.
Like a carbonyl compound, or it's like state 0.
Okay. And we even broader. Right now, we are thinking only on the first 2 rows of the periodic table. Which elements, if you brought in other specific situations, materials composed of such elements that electrons will get paired?
Rubium, cesium, yeah, for laser.
Good. Cesium? Yes, doping of semiconductors. Yeah, it's absolutely true. And this is good doping of semiconductors. And what else? One can dope semiconductors with the object that I'm going to bring on in the next minute. But maybe you can guess it. What is inside the compass?
Oh, a magnet.
Yes. So what is the reason of a magnetism?
They have unpaired electrons.
Exactly. As soon as you need to compute something about magnetism, this protocol will not work, right? Or even small materials that have like iron as a typical magnet, or manganese, or a lot of transition metals and actinides and lanthanides have unpaired spin. So as soon as you deal with magnetic materials and unpaired spins, you will need multiplicity.
Because all these spins are up and down.
Yes. Unpaired spins, right? If originally this area of knowledge, computational chemistry, was designed for chemists, today it is for everyone, right? And in traditional chemistry, what are the objects where unpaired spin transition metals are playing role? Like traditional chemistry doesn't deal with like quantum dots or bulk semiconductors or magnets. It deals with molecules, but there is a class of molecules that include transition metals. How are they called?
Photomics.
Huh?
Photomics.
No, it's application, but maybe Rebecca could help us. If there is a metal and several organic ligands around, what's a common name? It's when there are many metals, but for metal organic frameworks you also need this multiplicity. If there is only one metal. Yes, crystal field theory is exactly for these objects, and they are subject of study in inorganic chemistry. Metal, organic, it's so complicated, therefore they named. First letter is C, second letter is O. Metal, organic, yes, complex. So if there is a unpaired spin metal and some close your ears if you're a chemist, some organic junk around. Ligands that coordinate and stabilize it and make it allow it to perform some chemistry. So it is a noticeable fragment of molecules and materials that need special treatment. And when I will mumble something, if you're bored, you can just go along these protocols and try to do things. I'm just entertaining you and giving general context, but I'm not sure how important it is. So when there are unpaired spins, there is a convention to call all spins that have arrow up alpha and call all spins that are arrow down beta, right? I think we had like lecture 9 or 10 with focused on the subject, and you were performing homework on spin up, spin down operators for one spin, right?
Focus.
Yes, exactly. But what if you have like 100 of spins? We just label alpha up, beta down. Originally, when we had 2 electrons per orbital, we were assuming, and I am assuming it at this figure, which is wrong. I'm assuming that energy E sub I for electron with spin up and electron with spin down is the same. There is no theorem that states that. The energy for molecular orbital with spin up and energy for molecular electron for spin down could be anything. And more general picture would be to do like and then we will call like energy I comma beta, energy I comma alpha. Okay, so if you are okay with this picture, then you got the background. When you are preparing Gaussian input as text file without Gauss view, there is a second line in the input file that tells which method to use. Typically we do drop-down menu and just tell Hartzyfock or whatever, or one can type it, 2 letters. If you add letter U in front of the method, it will automatically go from this simplified picture to more general picture. U means unrestricted, means there is here there is a restriction that spin up and spin down on the same orbital number will have the same energy, and if you remove this restriction, then it is called unrestricted. Okay? Then density of states for alpha and beta spins will not coincide. And one of the typical visualization of density of states is plot it up and down, like alpha up, beta down. And they may diverge. If you look into this handout, it shows this, right? The orbital, yes, please.
So far we have done for this up to this class. The DOS has been done taking two spin the same energy up and down.
Yes.
But this is wrong.
Yes. The one orbital, each given orbital was having simultaneously 2 electrons or 0 electrons. So all spins were paired. And now we need to go to the domain of unpaired spins. Okay? The shape of orbitals, of molecular orbitals for alpha and beta orbitals may also be different. Sometimes they coincide, but there is no theorem telling that this orbital and this molecular orbital should have the same shape. So the Hartree-Fock procedure and later all other theories may have independent procedures for alpha and beta spins. Now, which example I suggest us to pursue? And again, feel free to go ahead and just follow the steps. I'm very slow, and you can be ahead of me and complete everything what we have to do today by this time. It's like 5-10 minutes. I am suggesting a model which will have our friend titanium transition metal ion, which is at the beginning of the third row, right? It's a transition metal that has d electrons. And before we were playing with titanium hydroxide, which it was coordinated with hydroxyl groups four times. There is another stable configuration for this metal when instead of 4 it has 6 coordinating ligands. And I'm using the notation used by chemists to highlight the three-dimensional nature. So thin line means it is same distance from us. Thicker line means it goes to the class. Dashed line, it means it goes outside, right? And then here we put oxygen, 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 and put 2 hydrogens. In our previous attempt, OH group is typically minus, right? And when we had 4 of these groups, and it was pulling electron from titanium, and it was becoming 4+. What is the oxidation of water molecule? Is it charged or neutral? Neutral, right? So if we believe that titanium needs to be 4+, we need to take the whole structure and put 4+. Right now, we do not have time to make this little experiment, but I assure that 4+ for this structure will not converge, or the structure will explode. It is not stable for 6 coordinated. But if one makes it 3+, then the structure will be stable. In the nature, in experiments, this corresponds to solution of the titanium chloride in water, right? The chlorine, it dissociates, and chlorine ions floating very far, or maybe nearby, but the water forms coordination bond and make this highly symmetric structure. So if chlorine is minus, titanium is 3+, it is chemically stable. And in order to save efforts, it is very common motif in computational chemistry efforts to assume that these counter ions are floating somewhere, but instead we just assign total charge of the system being non-zero. Okay? Now, for the planning of this calculation, I may want to go to the P table that we did sometimes in the past. P table. And look for titanium. So titanium should look like argon, and on the top of the argon there are 4s2, 3d2, right? Please object if you disagree or if you need more comments. The aufbau, which means build up for the titanium 0 is the same configuration as argon, then 4s2, 3d2, right? If we do 3+, it means we are removing 4s electrons and 1d electron. Before we remove T0, all spins were paired, right? But if we are doing titanium 3+, then it will be argon and then 4d1, right? So only 1d electron. So total number of electrons is unpaired. And this will be a situation when one cannot use closed shell paired spins. So on experiment it is a slightly magnetic purple solution. So the goal for the next half an hour is to build the structure, set up charge and multiplicity keywords, then observe this type of structure, plot density of states, plot molecular orbitals. There is one more piece of background information. One more piece of background information. Please help me, if you can, to describe what is multiplicity. If you're not sure, just give examples which values multiplicity can take. Huh? Oh, thank you for being brave. Yeah, there is nothing wrong. Multiplicity can have multiple values. Sure.
It's up or
Huh?
down. It can be up or down.
No, no. So when all spins are paired, one calls it singlet. When there is one unpaired spin, one calls it doublet. When there are two unpaired spins, one calls it triplet. And for the rest, I do not have enough intelligence to continue. Did you hear this word before? So how come, I probably right on the other part of the board. So one unpaired, all spins paired, 0 unpaired, number of unpaired, 0, name is singlet. one unpaired name is doubled. Two unpaired, the name is triplet. It sounds like someone intentionally wants to confuse me, right? What's the logic? Like, why it cannot be zero flat? 0, 0, 1, 1. Why it is like, and here it goes, it changes, right? So what's the logic in this notation? So if spin takes values of 1/2, let's put one more. So for 0 spins, as 0. For 1 spin, it will be 1/2. For 2 spins, when add together 1/2 plus 1/2 will be 1. Okay, and divide by Planck constant. So it comes the value of spin is identical to angular momentum takes value Planck constant over 2. Okay, so at least here there is a logic. Right? Now, if it is a singlet, if there are no unpaired spins, you cannot do magnetic experiment that will change configuration of the system, right? So it's single, it's only one configuration. It's unpaired spins forever. If there is one unpaired spin, then by applying magnetic field one can flip it. So the total value of the spin, absolute value, is 1/2, but the projection can be either plus 1/2 or minus 1/2. So 2 values. So how many projections? Here is 1. Here are 2 projections, up and down. 2. If the total spin is 1, there is a quantum laws for finding eigenstates of total spin operator, and same as Schrödinger equation, it gives discrete answers. And for triplets, for spin 1, it can take 3 values. Both spins up, both spins down, and then symmetric configuration, then like 1 up, 1 down, plus 1 down, 1 up. So 3 configurations. Up, both down, and up. Down plus down, up. So first, second, third, 3. Okay? So it's number of, what do you say, replicas with the same absolute value spin, but different projections. And there is a number, there is a simple formula that gives this. If we call this stuff with letter S, and we call this one with letter M, and let's practice, let's try to practice let's practice this equation. So if you set yes, plus 1. So if you plug in S equals 0, what will be the M? Huh? 1. If you set up S equals 1/2, 2. If you plug in S equals 1, good. So it is a connection from this column to this column, right? So this one is absolute value of spin, or absolute value of Z. And this M stands for multiplicity. So how many multiplets is available for given spin configuration? Why I'm wasting your very precious and mine, maybe a little less precious time on this failure case? Because Gaussian will fail if you do not give him multiplicity. It's a stupid robot that needs a help of a wise human. So when we sometimes it may pick the suggestions from the database, but it will not always be correct. So if we look into
I have a question.
yes, please.
Why the two spins are up and down? The two spins, both are up and both are down.
I hear you. I hear you. I'm just refocusing the screen. So if both spins are up,
Yeah.
it's perfect.
But we know that in an orbital, one spin, if one spin is up, another should be down.
No, there is a way to request that two spins will be up. It will be more than 1 ampere spins, and for magnets it could be like 100 ampere spins.
Okay.
Okay. So it is the files that we will create, and maybe those of you who are not wasting time on listening and doing practical things are already there. The standard input file has before we go to the coordinates, has numbers 0 and 1. You may double check in all files that you are doing calculations. If you look, if you do like more or VI of the files, the two numbers in front of the coordinates were 0 and 1. What do they mean? And what are the names for this? Yes?
0 times 1.
Exactly. So 0 means, well, we have a lot of nuclei, a lot of electrons. They have a lot of charge. But 0 means number of positive charge equal to number of negative charge, right? Multiplicity, 1 means singlet. All electrons are paired. But if we want to make 3 plus, we put 3. Then we know from chemical intuition that it will be doublet, 1 unpaired electron, which can be up and down. Therefore, here is the number 2. Right? If it would be, if you would make a configuration that will take triplet configuration, one would put here 3. Okay. If you are looking for electronic paramagnetic resonance, well, it also related to nuclear magnetic resonance, then this game with spin and multiplicity is of importance. Okay, so I'm going to build the model and set up a calculation.
That was an octahedral.
Huh?
That was an octahedral plutonium, or
It's hexa aqua titanium.
hexa.
Hexa. The previous time we did titanium hydroxide, where it was 4 coordinated. This one is will be 6 coordinated. And if you do not like manually modifying input files, one can put things here. But before, let's build a model. So I'll try to build it from scratch and then go over and make sure that you all have it, because it is a little challenge. Yes?
So if the charge equals to 0, which means the number of positive charge equals to the number of negative charge.
Yes, exactly.
Or what about the charge equal to 3?
It means positive, 3 more positive than negative. It means we removed 3 electrons from the system. For this specific example, we could just put 3 chlorine ions around, and then we do not need this 3+. But there is so much uncertainty how far, on which distance, in which configuration. So in average, we can replace these 3 chlorine anions just by putting 3+ here.
If we remove many charges, what about if we add more 3? It should be
-3. Yes. So it is anions and cations, like for Koopman theorem, if you need to do ionization or affinity. So I am going to do Gauss view. So if I'm selecting titanium, there is titanium octahedral. So Gaussian has prompts for different coordination numbers to start with reasonable geometry. So previous time we were taking the tetrahedral. Now we are taking octahedral, which has 6. Again, there is an impression that someone is trying to decept me. There are 6 ligands, but octa means 8. So why?
That was my question.
Anyway, yes?
Because it forms an 8-sided shape with the 6 points being the vertex.
I agree. Does anyone agree? Does anyone understands this? Huh? Make sense? So, if we if you take a piece of paper, right, planar structure, and we draw four lines, it will split the space onto 4 segments. If you take a space and draw 3 planes, there will be 8 quarters, not quarters, but octa something. So this 6 axis makes 1, 2, 3, 4 on the top and 1, 2, 3, 4 on the bottom. Total 8 things. So titanium octahedral, I'm clicking, and now I am trying to put the oxygen. Maybe I'm putting oxygen, but instead of making water, it does something that I do not. It does this hydroxyl. So I have a way to fix it, but maybe you'll find something more elegant. I'm putting nitrogens, saving the file and then replacing it to replacing name of atom to oxygen. It will be a slightly different distance, but it is a good start. And if you need productive results for real science, we need to optimize. Right now, today, we'll go without optimization because we need just qualitative thing. So,
so the values are oxygen here?
huh? Wait, I'll show. If you put oxygen, it will miss the hydrogens. Yes. Right, because it doesn't believe that the system can be correct. File, save, titanium, 6H12 class. And now I can open it in the I can open it in the VI and edit it, and just as soon as I see nitrogen, I replace it with oxygen. Okay, so this is the structure. When if I will decide to optimize it, it may change, but I do not want to waste time on ambiguities of optimization. I just need an example.
How did you connect the hydrogen, two hydrogen to one oxygen? Is it possible to do just?
It is what I did. I placed their nitrogens.
Oh, that was cheating.
Yes.
I can do it with Gaussian, just choosing the oxygen atom and replacing the nitrogen atom. It's going to be same.
Well,
No.
for me, it was working only in command line. Because if you click back on the oxygen, Gaussian thinks that is that just a second, that oxygen must have two bonds, and if one bond goes to titanium, the second one goes to hydrogen. There is no third one.
Yeah.
These are oxygen, right?
Yes, it is a good thing. Can you come and show?
I still need another hydrogen.
So
Do you want to do magic?
no,
Like that?
no. Far from that. Then I did this,
Super.
yeah, and then use the broom and then do optimization.
Thank you. Thank you.
Okay.
So how much will you check the hydrogen?
And now we need to set up calculation. So I'm not going to do optimization on the energy. Since there is a transition metal, I'm selecting this 102DZ. And someone, probably Raju, will explain what are this 321, 631G. Okay. And right now it tells charge 0 and spin singlet. If I try to do it, it will panic or give wrong results.
What is the meaning of charge 0 here?
Huh?
What is the meaning of charge 0 here?
There is no meaning. It's just when I open the window, it has some preliminary data. It goes through prompts me to use this value, but it's not right. I want 3. Yes?
Wouldn't the charge 0 refer to the overall charge molecule in this case?
If we would put charge 0, it will mean that we mandate titanium to be in zero state by bringing more electrons, and then if we do optimization, it will explode because it's not stable. So it will repel these water molecules away. So it will be not a dissolved ion, but it will be like metal with water trying to approach it. It will be different chemistry. Yes? No. Salim did a broom, but right now I don't care. When you do it for homework, if you have like few minutes more, it's good to optimize. But Hartree Folk is not the best tool for optimization. DFT is better, yes. And I'm going to save. Tell that it is HF energy. Now, if I'm looking in the directory, so it puts the numbers 3 and 2. Just in case, it will be more safe to put the letter U here. Sometimes it recognizes that if spin and multiplicity are away from singlet, that one automatically does this U, but it's better to specify it. So unrestricted Hartree-Fock. How do I submit Gaussian? What should I type? Right? And probably I should use the ampersand symbol.
So what was the next step?
Huh?
What was the next step after?
Looking on the orbitals. So after it is done, you do see this log and check files. And if I'm looking onto this log file, I'm observing. Oh, give me a sign if I need to go around and check that you are on the same page. Or everyone is so experienced that you are doing it ahead of me. Everyone is good?
So you have to run in the
I didn't get the last comment that you used. What was that? G09? What are you doing here?
Submitting this input file to Gaussian and forwarding the output into the same file name .log.
But you already had the log file. What are you
No. I did it first and then log file appeared.
So this is different with the file that you submit with Gaussian, with the visual interface? I get confused with that.
No confusion. Visual you can go and submit with visual, as you call it, visual interface.
For
Like-
this you had a log
Yes.
file, right?
Wait. I click here, submit. And instead of submit, I can do just save.
Okay.
Why I'm doing it? If I do submit, it will go into Gaussian immediately and we will do calculation.
Okay.
But here we are doing very small models for exercise. If it will be productive calculation, and we submit them all from this visual environment, it will kill the server. The typical work environment, if you upload the text input file onto the powerful high-performance cluster and then submit it in a command line. Okay?
Okay.
And starting from the next week, we will do more and more high-performance computation on clusters, and we will have less and less visual stuff. Also, I will announce it again, but please consider to bring your own laptops to the next meeting and for the rest of the year. It is not mandated, but you'll feel more comfortable.
Sure.
Okay, so after this one is complete, there appears the log file. And now I'm going to look inside this log file. I'm typing more, and then going what it shows. So I'm looking forward to see this virtual and occupied segments as we did before. And what I see. So in addition to ok and virch, there is a word alpha. And if I scroll forward, there is a basically repetition of the same keywords, occupied and virtual, but they have this beta words. And this is the main difference of this unrestricted thing. Let me walk around and see that everyone is on the same page, and then we'll continue. You do it just once. Oh, okay. It will take some time, and after this you can put a symbol, and then it will not block you from typing other commands. All good?
No.
What is it?
I built the molecule,
Uh-huh.
typed the VI, and then when I named it, and I got this.
Okay, let me try something. Have fun with your charge.
Yeah.
So .com if you need input file. It hates spaces. So try to replace spaces by underscore, then it will be a little more natural. So here is the input file, and I think you already have this output files. So there are alpha and beta. Just watch them and enjoy how they look like. Yes?
Why can't they submit the final version?
You did it. All good?
Yes,
So did we use this charge and spin arbitrarily or something like
What?
Did we choose this charge and spin arbitrarily?
No, spin orbital. Multiplicity, spin multiplicity.
Okay, this is the okay.
All good? Yeah, good. I don't see any. Maybe you're doing something more fun. Oh, okay, okay. You're ahead of. Thank you. The numbers in here, this 0.01, if you replace it by 0.05, figure will look nicer.
Okay.
Well, right now it's just like educational drill, but if you do it for productive, it's larger number will make it more beautiful.
Okay.
All good?
Yeah.
You can put this symbol at the end, and then it will not block you from typing other things. Okay, I see you. All good?
Yes, sir. I don't know how to quit from the
How to-
VI.
Oh, how to?
Yeah, the color.
Oh, how to exit? Escape. Escape.
Oh, escape.
Escape.
Okay, escape first. Then colon QW.
W. Okay. Yeah.
Yeah, WQ. Oh yes.
I
All
can
good at
just
the
quit from the server wrongly.
Oh, you got disconnected and you're
Yeah.
connecting back.
It's okay.
So, what do I do if I see these numbers? The same as before, it's too many to watch them by human eye. Here I just copied them, the list for alpha and beta, and by naked eye I see that occupied and unoccupied, the border between unoccupied and unoccupied, happens a different number of electrons. So here it goes 1, 2, 3, 4, 5 by 1, 2, 3, 4, 5, 6, 7. 7 by 5 will be 35, right? And here it goes one less. So there is one more occupied orbitals in the alpha domain than in the beta domain, right? So this one will be orbital 35, highest occupied alpha. Homo alpha will be 35, and Homo beta will be 34, one less. Therefore, for alpha it will be one more. And if I watch these numbers, their subtraction will be about 1/2 in the Cartier units, and it should be about 13 electron volts in regular units. This is not something that we can trust. We are not going to use Hartree-Fock for any productive analysis. If one optimizes geometry, if one uses more modern methods, it will come down to like 2.4 electron volts. But generally, all these numbers are negative, which means system is stable, and we can go and analyze how density of states, how to compare this list of energies in a more visual form. So there is same command as we did before for singlets, with the only difference that there is a underscore alpha, right? So I'm going to apply the same script script to the file, and here I need to use the file that came out of the So Perl, name of the script, underscore alpha, name of the file that was generated by Gaussian, and then this grid points, width, electron volts before, Homo electron volts after Lumo. Hit enter, and then if I look on the files that were recently generated, there is a file that is named DOS alpha. And for the beta electrons, I need to repeat the same procedure, but to type the keyword beta. If I check which files have been created, you see this DOS beta. Since same as in the previous lab, these two files, DOS beta and DOS alpha, can be plotted using regular Excel or Origin, but we will be using this GNU plot just to save money and not purchase licenses. For the script, I will rename DOS alpha W into more generic name DOS alpha.log, and I will do the same for beta. So after this operation, there are two files, DOS beta and DOS alpha, and they have like substantial amount of bytes. So I will do one more command and then make a turn around. So we are doing this GNU plot if I'm curious, I can look inside the script and see that it just plots DOS alpha and DOS beta into this file named DOS spin, and upon completion of this command, there is this DOS spin 09. So since it is in PostScript and I need PDF, I can do PostScript to PDF conversion, and now we have this PDF file. So in order to watch this file, I will be using the mouse operated command, but generally please do not forget the ways to transfer files with command line. Starting from next week we will be using it more and more because we'll be using remote HPC cluster on a regular basis. So what we have right now, there is a list of alpha orbitals occupied with this energy, unoccupied with this energy, and a list of beta orbitals which are accumulated shape because of this delta functions. And we do see the idea that we were discussing at the very beginning, that energies of orbitals of the same index for alpha and beta do not coincide. Right? And this is not wish or calculations that has been made to fulfill any demand of applications. It is just how the nature has constructed it. You just need to accept it and take it into account. So if there is a unpaired spin, one needs to use spin polarized calculations. Understood? I'm going to make a circle and make sure that everyone is on the same page. Everything's good?
I lost track now.
Huh?
I got till here, but then the next commands that you used, I lost track.
It's all.
Okay. So, which one do I understood this one, but before that.
Let's. Do you have that this file open on your? It was in the email.
No.
But you can open and copy paste things.
Okay. So I start from here. Where do I start from?
You just do it one by one, and it should give this image.
Okay, I thought you used another command.
No.
Thank you.
I'll please show me when you're ready.
Okay.
I'll come and
This command line, right?
Mm-hmm.
It'll take me a while to type that in.
You don't need to waste your time on typing it. You can download this file into electronic form and copy paste.
You might use that today.
Yes. So the Word file is this one, and PowerPoint is what I'm showing.
So just copy and paste the top line.
Uh-huh. Paste. Just hit enter. And now okay, it's beta. And now you can copy paste from there, but I'll do. So the name that you used was web 7 space network. Okay, better. And now we need to do so Perl, name of the script, name of your file, and then parameters. Now we do ls minus lt. See this non-zero. Something didn't look. files are non-zero, which is a good sign. And after this, we need to rename these files, which will be unique for everyone. Those beta something, those alpha set. We need CP, those alpha. Those alpha. And the same for beta. Good. And after, let's check the other files here. Now we are doing this. So the PDF file should be there. No. See, those spin PDF. So we need to go to EWD. Kilin shared. Shared. Okay. Yes. You ready?
No, I used to that screen.
Wait. Everything is good, but we shouldn't rush. So these commands are for this figure. When you get to this point, then we go further. The name of the file in here is unique for everyone. You should have the plug in and substitute the name of your files here. It complains to no such file.
Yes.
So let's do. So instead of this name.
How did I get this?
What?
I can create this. So it's.
No, you probably copy pasted it from. So here in this command. And then it should be space here. Space, and then the script, space, and then this one, right? If you really look nicer. Okay, then we do the same for Peter. So we do have this beta and this alpha. CP dos alpha dos alpha dot log. those people. Know this thing that you're comfortable with.
Wait for the time. Can you come earlier tomorrow to discuss something and prepare the video?
And then we need to convert it. I'm just trying to go for this path. My pleasure. All good? Okay. So you know how to do this ESP maps?
No, this is the spin thing.
Okay, yes. And do you know how to visualize this potential?
No.
I'm also having trouble with this, if you want to figure it out. So I need to download both density and potential, and then try plot density first, and then map second potential over the density.
Okay.
I will try it there when it will be time, if you have patience, but maybe you can discover it before.
Okay.
And you did the orbitals, right?
This one?
Uh-huh. Do they look alpha and beta similar to each other, or they have a little bit difference?
Oh, they are different.
Yeah, which is natural.
Yeah.
Okay. All good?
Yes.
Density of states works well for you?
Yes. Could you repeat again what's the relative plasticity? It should be the single equals to double means 2. One is single.
Degeneracies. How many configurations will give the same energy?
How many configurations will give same energy?
Yeah, right. For singlet it is only one. For doublet, it's if the energy doesn't depend on spin, we can flip the spin and have the same energy, 2 configurations. For 2 spins, there will be 3 configurations, and if you go further, it will increase. So multiplicity is how many multiple copies of the system will give the same energies.
How many configurations?
And for this basic quantum things, Wikipedia gives very good articles. So you just look for Wikipedia multiplicity, but you'll see the same thing. Amir, you've got the dose, right?
Sorry?
Density of states works well for you.
Yeah.
Good. So what is the next goal? If your time is up and you need to depart, it's fine. Things are recorded. So now we do need to explore whether the molecular orbitals of the alpha and beta configurations will look similarly or different. So if you look, the procedure is very similar to what we did before for closed shell configurations. So we need to convert. I'm not tall enough. We need to convert the dot check file into form check. fchk. So type form check, the name of your file that ends with chk. And after this step, there is a tool, command line tool named kubegen, and this is a copy from Gaussian web page. If you type in like Google search kubegen, you will be navigated to there. So it gives the syntaxes. So you type kubegen space kind what you need, form check file, and then the file where you want to forward your output. Density of states worked well?
Yes.
Okay. And we are starting from molecular orbitals, and if we need, if we know for sure that our system has spin polarization, if it is unrestricted, then instead of MO, you type AMO equals N or BMO. So it turns here AMO, BMO. And we will practice this molecular orbitals for some time, and after one may practice some other options of this kubegen. Like one can put density, which is charge distribution of all occupied electrons. One can do density only for alpha electrons, one can do density only for beta electrons, one can subtract them. And then basically it will give the orbital where unpaired spin sits. And the potential is something that is not straightforward to plot, and for my research I never was needed to use it, but some traditional chemistry calculations, some traditional chemistry clients of calculations need this. So the potential means the mean field electrostatic potential created by all occupied electrons. Why it is needed? Because at some regions potential is smaller, for another is bigger, which means where electrostatically the molecule will attract other agents and where it has affinity to participate in chemical reactions. So, based on the list of orbitals, the number of highest occupied for alpha is 35. Number for highest occupied beta is 34. So we may want to plot a couple of orbitals in this range. So maybe from 34 to 36 for both alpha and beta. So after typing this form check, I was typing this kubegen orbital, alpha molecular orbital, the number, name of the form check file, and then space, name of the cube file where I want to forward this information. Please give me a little sign if you didn't make this procedure. Okay, please raise hands if you completed this procedure already. Huh? Please raise hands. I just need to navigate whom should I visit. Who has done these commands for today's? Keep hands lifted. 1, 2, 3, 4. You didn't. You did. You didn't. Okay. So after, and it's probably time for me to make a circle and to instruct in this. But after these commands are done, one can open these files in the Gauss view and build the select cube and build the isosurfaces. Then one can do it for each of these orbitals. So please try to practice creating these files and visualize them and look how they are similar or different. I do not promise that there will be extensive homework on this, but we will come back to this philosophy again and again with different software. So it is an important stuff. let me bring this commands, and I'll start circling and visiting. Something urgent? No? No? Yep.
So presentations are tomorrow, and I'm just make sure I'm presenting on stuff like Hartree shock and the different types of those formulations.
Mm-hmm.
Okay, and so I'm going to take the GRE on the 14th, and I was wondering if you would write a letter of recommendation for my application.
Absolutely, no
Okay,
problem.
thank you.
Send me reminders.
Yes.
I'm very willing, but I'm getting like more tasks that I can complete. So to help your task being on the top of the list, I appreciate reminders very much.
Of course.
Okay, it works. You don't need to waste your effort on everything. You just arrow up and just place 5 here. 5, 0. Okay. Yes, exactly. Yes.
So
You-
but this this one, like, is it necessary?
The name of the file is individual for anyone in the class. It is yours.
Yes, I did. I have my own, but then like this
Form
line,
check?
Yes. Is it necessary to do like before everything else, or?
No, you can do this command can be made at this spot.
Okay.
For this density of states, you do not need to do this form check. I was just a little absent-minded and typed things quickly.
Okay. Because this one was done even before we calculated.
No. This one is in order to do this command, we need to do this one.
Yes.
So this command can, like, if I edit this file, I can move it into here. For the density of states, you.
Okay, it's just this.
Yes. Okay.
Okay. So.
This form check is for orbitals, not for density of states.
Okay. It's only for orbitals. I see. So we don't need. Oh, it's totally different. Sorry, like. Okay. I see. It makes sense now. Yeah.
Okay.
Yeah, it makes sense. Okay. Yeah, I believe it's working now. So I didn't check it yet, but after.
Type them and then try to draw them. For me personally, it's most attractive part of all this activity. Just drawing orbitals, it's aesthetically pleasant.
Yes.
It is, bro. Did it send you the picture or?
If you feel bored, I will compose a little homework for the weekend. But right now, please select preparation of your slides for tomorrow as a primary task. If you have already made your slides, you may revise what we did in class and update them. And we didn't cover the density and ESP map yet, which is kind of your thing.
No, for me that was not a spin. I was went through the ESP and also.
Yes, density.
Yeah.
Did you do it already?
Electron density. Yeah, I put some Gaussian examples, for instance, for a benzene ring.
Can you do it for this model and add them to the slide?
Yeah, I will.
I think then I see you have a strength and energies, so we need to use it.
So for instance, I just get confused with the putting the charge. Okay, for this we don't have to do any calculation or
no, it's already
optimization.
no, it's automatically there. You just need to know which.
Before doing any calculation, we know
No,
charge, right?
no. After you do single point self-consistent field like Hartree Fock,
Okay.
this information is available. Do you know how to get these numbers?
Yeah. For instance, for this model, let me open the. Oh, you're right. I did the calculation first. So
you need to open the check or form check.
this one, check file.
Mm-hmm.
For instance, this So from the chart, chart distribution. So that was the, how do you name it, molecule? So just show the numbers.
And
also there is atomic.
Yes, but you may want to explain what those numbers mean, where they're coming
I
from.
put them. Where are they come from? It's a little difficult, but I put the meaning of the number.
Did you remember
You mean the
handout that I was sending before last lecture?
Yeah.
About density metrics for Hartree-Fock,
Yeah.
with this expansion coefficients squared. They basically give this the expansion molecular orbital expansion coefficient squared give this Mulliken charge.
that formula, but I didn't put in the presentation because I just wanted to make it visualize than the mathematic formula. What's your opinion?
Formulas are cool.
Okay, I will.
Because when if you do not send me an email like I'm so shy, erase my recordings from the whatever, and you will watch it in 10 years from now, you appreciate equation more than visualization.
Okay, I will.
Just a second, I'll check. Okay.
So could you say so?
But the names here could be different if you were. LS.
Yeah, so I think we do have these files. These ones.
PWT.
So what did I do? I copy those files.
Okay. Yeah, I see. Good. Did you find the way to upload the ESP map?
Like this.
This is I can do as well, but
Yeah.
can you do 3-dimensional?
3-dimensional.
I know it is not easy, but let's try together. But I do not guarantee success.
Okay.
Okay. No. Oh, density and penetration. So. And now. So if you try to do it maybe for some models it fails, but if you do it for closed shell without the spin things, then this map will become colorful and will look very nice. It will look like a complicated flower.
Okay, and what does it tell me? Like, what does it tell me if I put
the meaning, if you're able to do this electrostatic potential map, it will range colors from like blue to red, and it will mean electrostatic attraction or repulsion, like different sides of the molecule able for like electrophilic, nucleophilic attack. And by looking on this electrostatic map, you can tell, okay, your reactant will approach from this side. And
okay.
So
yeah, that makes sense.
I don't care, but many organic chemists like become absolutely happy after seeing this map. So maybe it makes sense to try it for some closed shell.
Okay.
Maybe the one from previous homework for this hydroxide.
Yeah. Okay. Thank you.
Yeah, thank you. Are you able to get orbitals?
I lost track.
Oh, that's. I will be back with you.
I didn't make it because it didn't show it before.
Wait. Were you able to make the density of states?
Yeah.
Yes?
I have a question.
You did it?
Yeah.
So you have problems with orbitals?
Yes.
Okay.
This is the thing I got.
Okay, so you see it a little bit different.
Yeah, and I have a question because for this one, the first you didn't show the form check. You make it later. So when you plot the contour.
So for density of states, you do not need form check. Form check is needed for
the orbital.
Yes.
So when did you make the contour? So this one, if this contour taken all those two files?
Mm-hmm. Only two files, nothing else.
Nothing else?
Correct.
That's why I'm asking how this is taking the one alpha beta. He's taking both alpha and beta.
Yes.
Okay. So now I lost it. After that I went outside.
Oh, okay. You just need to copy paste these things. For the future, if I'm starting to mumble something that away from what you're doing, please stop me. I probably was too excited about typing things myself, but do not hesitate. Do not be hesitant. Like, stop. We lost track.
Yeah, I went outside.
Okay. So we need CH key and FCH key. This is non-zero. Okay, good.
But if you check the energy file, it's showing singlet.
No. Always good.
No. I'm not talking about this one. The energy file, E underscore. The orbital.
Don't. I was not instructing you to look there. It's just a byproduct of the procedure. Do not trust it.
Okay.
Do not trust it. Do not look there.
Because is the 1100, I didn't find 1100.
I'm the code writes writes number 2 instead of 1, but it's just because the code is underdeveloped, and this is only illustration.
Okay.
You don't need to do it. All done?
Yeah.
Excellent.
I will try to add them.
Because it's not visualizing me on your shoulder here, like.
This wait. I understand, but the information here is sufficient. So you see.
Alpha and beta.
So you just count 5 by 7, 35, right? And here 5 by 7 minus 1, 34. That's it. You don't need anything else.
Okay.
And now we just practice.
I just you practice a cube gym.
Yeah?
Yeah, I can do that.
Okay.
Because I was just hesitant, I was just confused.
Okay.
I'm not getting 1 and 0.
Okay.
No, I'm getting 2 and 0.
I
already submitted the
Mhm.
homework for this. It's the same thing for this one. Homework service.
But do not look onto this E sub. Do not look on this file. It is not yet developed. Uh-huh. Mm-hmm. Okay. All good, or is there some?
Yeah, it's just
For which one? I am getting this problem for potential as well. You're not alone. For potential, we may want to try another model with singlet configuration.
Okay.
If you open older, like go to directory or do homework for hydroxide and generate this potentials there, it should work.
Okay.
I will try it on the board if there will be time. Yes?
I cannot count from the 30, 50, 35, I have to count from here.
Yes, exactly. But you get the same number, 37 and 35, 35 and 34. Right.
What do you have to do here?
Okay. So. Okay. And if you think it takes too much, you can remove it. Put the number. Now it shows that most of electrons are on water and oxygen and a little bit on the titanium. How things are going? Orbitals going well? So everyone was able to do orbitals, right? Good. Yeah, probably this maps will make sense only for unsymmetric molecules, because this one is quite symmetric, and for reactant is equivalent from any side to approach. So it has this blue stands for excess of electron, so anionic oxygen from each side, and if the titanium would be outside, it would be red because it is depleted with electrons. I think, I need to show the Mulliken charge, and then that will be done for sure. So by clicking on charge distribution, so if you load check file and click on charge distribution, there will be, by definition, Mulliken, which is just square root of the expansion coefficients of molecular orbitals over atomic orbitals. It's not always correct, but it is a good starting point. And in order to do other sorts, which NBO is a really good one, needs to use other keywords in the input file. And one can show this numbers. So it tells how much the charge on individual atom differs from neutron. So on oxygens, it shows something like -0.8, which means it's almost minus means negative electron, and almost the whole additional electron is sitting on the oxygen. On hydrogen is 0.5. It means that about half of electron were withdrawn from the hydrogen. And we know that electrons are discrete, but wave function density of electron is protruding towards oxygen. Therefore, in the space area near the hydrogen, there are less electrons. And on the titanium, there was like 1.6 positive charge because electrons were withdrawn towards the oxygen. If one is analyzing like charge transfer and donor acceptor things, it can be useful. Also, if the model contains too many atoms and there is no chance to watch these numbers, which looks, it's too much information if there is 1,000 atoms. There is an option of color, and then it shows, assigns the redder, more red for anionic and more bright green for cations. So you can immediately identify where a cation is.
How you do that?
So you need to open check file for your calculation, and after you do it, you go to results and select charge distribution. Yes.
So I don't have a question regarding these charges. So we are doing the molecular dynamics, the next level. So
Force field or
force field, yeah. So for the force field, we need to find the electrostatic partial charge. So are this
No. It's for electronic structure. It's not for forward force field. It's for electronic structure when electrons are explicitly treated. evaluation, but it is not literally what you do. Were you able to make this? Okay, I think it is the best we can do. And it's, it shows one church on this side, one church on the other, which is reasonable. The same like mushroom for Alice in Wonderland. Which side of mushroom is better?
I got actually.
Oh, you're trying to.
Yeah, I tried, but I got 40. This is after this 8. 68.
How many atoms do you have?
I have titanium, oxygen 6, and hydrogen 2.
And what's your church?
Sorry?
Church. What is the church in your model? You need to do 3 plus.
Yeah, I do.
Okay, it's still
I really 3 and 2. But
or you use different bases. Yes. And it is, by the way, your subject of presenting. So, depending on the basis set, number of orbitals can be different.
so for the basis set, if I run it from the terminal, it will take the automatically the first one?
You need to manually select the basis set that is feeding your.
So I have to do it here, right? From here.
Yes. This one is.
So I can select this one. So if I run from the terminal,
then it will be the same as
this one. So
right.
this is the system. I got it.
So and anyone is free to leave. We are over the time, but I'll stay here to answer some questions. So for the titanium, if we explicitly include all this all of these electrons, it will be a larger number. But for chemistry, we can focus only on the valence electrons and use some average potential for the core electrons. This will make a smaller number of these functions, and it will slightly reduce precision but make calculations quicker. For these small models, it doesn't matter, but if you go to like hundreds and thousands of atoms, all these little tricks are helpful.
It depends on the valence electron and how you which actually sub-level your conduction band is.
Mm-hmm. Yep. Okay, thank you for interest and dedication to the class. I look forward to see your files this evening by midnight. Let me know if additional information is needed.
I have a question.
Yes.
For the symmetric molecules that I'm going